February 9, 1944, Boxted Airfield, Essex, England. Lieutenant Colonel Francis Gabreski pushed the throttle of his P-47D Thunderbolt forward through the gate marked War Emergency Power. The toggle switch mounted on the throttle grip clicked upward with his thumb. Water injection engaged. He felt the Pratt and Whitney R-2800 engine respond as the anti-detonation mixture flooded into the supercharger intake. 2,300 horsepower became 2,500. The big fighter surged forward like a kicked horse. Then the engine exploded. Not a catastrophic disintegration that would send the fighter tumbling from 28,000 feet, but the unmistakable bark of detonation. The entire airframe shuddered. Cylinder head temperatures spiked. Oil pressure fluctuated. Gabreski's hand moved to the water injection switch with the practiced speed that keeps pilots alive. Off. Throttle back. Manifold pressure dropping. The detonation ceased, but the damage was done. Another R-2800 would require teardown and inspection. Another pilot would report the same terrifying result from a system that was supposed to give American fighters the power to dominate German interceptors. This was the third incident in as many days. Across England, at every 8th Air Force base where P-47 Thunderbolts sat on hard stands waiting for combat missions, pilots were reporting the same phenomenon. Engage water injection. Gain 5 seconds of emergency power. Then listen to your engine try to destroy itself from the inside. Some pilots had lost engines entirely. One had barely made it back across the channel after his R-2800 seized, trailing oil and running on 11 cylinders instead of 18. The order came down from 8 Fighter Command at 0900 hours on February 10th. All P-47 units were grounded for water injection operations pending investigation. Pilots could fly combat missions on standard power settings only. This meant no war emergency power, no 2,500 horsepower surges during combat, no ability to outclimb, outrun, or outfight German fighters when the engagement turned desperate. The Thunderbolt had just lost its primary tactical advantage, and nobody understood why. At Republic Aviation's factory in Farmingdale, Long Island, nobody believed the reports at first. The R-2800 engine equipped with anti-detonation injection had been tested extensively. Perry Pratt, the project engineer who had overseen the development, had witnessed hundreds of test cell runs without incident. Frank Walker, the development test engineer who had performed the initial calibration work, had personally adjusted throttle, supercharger, propeller, and water injection settings until the system behaved perfectly. The carburetor group under Dick Core's direction had designed and developed the water injection regulator and associated modifications. Everything had worked. The production engines leaving the Connecticut factory should have been identical to the test engines. Yet across the Atlantic, American fighter pilots were discovering that their emergency power system was more dangerous than the Luftwaffe. The story of how this crisis emerged, how close it came to crippling the American air offensive over Europe, and how one engineer's midnight discovery prevented disaster, begins not with the war in Europe, but with the fundamental problem that plagued every high-altitude fighter engine of the Second World War. More power required more compression. More compression generated more heat. More heat caused detonation. Detonation destroyed engines. The cycle was inescapable unless you could change the rules. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Water injection changed the rules. The concept was simple in theory, brutally complex in execution. Inject a mixture of water and alcohol into the supercharger, intake ahead of the combustion chamber. The water would evaporate during compression, absorbing enormous quantities of heat in the process. This cooling effect would allow the engine to run at higher boost pressures without detonation. The alcohol served 3 purposes. It lowered the freezing point of the water so the mixture remained liquid at altitude where temperatures dropped to -40 degrees Fahrenheit. It provided additional anti-knock properties similar to high-octane fuel, and critically, it prevented corrosion inside the engine's aluminum components. The system that Pratt and Whitney called anti-detonation injection had been developed under emergency conditions in late 1942 and early 1943. German fighters, particularly the Focke-Wulf 190, were demonstrating performance that threatened American bomber operations. The P-47 Thunderbolt had been designed as a high-altitude interceptor built around the massive R-2800 engine and an elaborate turbo supercharger system that maintained power output at altitudes where most engines gasped. But even with the turbocharger, the Thunderbolt struggled against German fighters that seemed faster, more maneuverable, more lethal than intelligence estimates had predicted. The solution Pratt and Whitney proposed was to extract more power from the existing R-2800 engine without redesigning it entirely. The shortest path to more power, as Frank Walker later explained in technical reports, was always more manifold pressure. Since the P-47 had a turbo supercharger which could produce surplus manifold pressure, it seemed a logical candidate for enhancement. The challenge was that additional compression of the inlet air generated heating, which resulted in power-limiting detonation. With the 130 performance number fuel available in early 1943, Pratt and Whitney was already extracting maximum safe power from the R-2800. Someone in the front office suggested water injection. It wasn't a new concept. The Germans had experimented with similar systems. The British had tested water methanol injection on Merlin engines. The fundamental physics were well understood. What wasn't understood was how to make it work reliably in a combat aircraft operating under conditions that ranged from sea-level takeoffs in Mediterranean heat to combat at 40,000 feet in North European winter. Frank Walker acquired a stock R-2800 Series B engine, serial number 5275, directly from the production line in early 1943. The only modification was a longer hollow bolt to accommodate a second banjo fitting that supplied water to the fuel inlet of the supercharger. He performed all initial water injection calibration manually, adjusting throttle, supercharger, propeller, and water injection settings until he understood how the system behaved. The work was methodical, exhaustive, conducted in the test cells at Pratt and Whitney's Connecticut facility where engineers could control every variable and measure every result. The testing revealed something remarkable. With the water-alcohol mixture flowing at the correct rate and the proper mixture ratio, the R-2800 could sustain manifold pressures that would have destroyed an unmodified engine within seconds. The power increase was substantial. An R-2800-59 engine, standard in mid-production P-47Ds, generated 2,300 horsepower at military power on 130-grade fuel. The same engine running water injection at war emergency power settings generated 2,500 horsepower. Some test runs achieved 2,600 horsepower with later improvements to fuel quality and injection rates. This wasn't incremental improvement. This was the difference between a Thunderbolt that could barely keep pace with a Focke-Wulf 190A and a Thunderbolt that could run it down in any flight regime. German pilots who had learned to make slashing attacks on American bomber formations and then escape using superior acceleration would discover that Thunderbolts could now match their performance. The tactical implications were profound, but there was complexity buried in the simplicity. The mixture ratio mattered. Too much water and combustion efficiency suffered. Too little water and detonation would occur despite the injection. The flow rate had to vary with power output. At 2,400 horsepower, the system needed to deliver 9.2 pounds of mixture per minute. At 2,500 horsepower, 11.5 pounds per minute. At high-altitude cruise power in high blower, only 7.8 pounds per minute. The carburetor modifications that Dick Corr's group designed had to regulate these flow rates automatically based on throttle position and altitude. The alcohol itself presented challenges. It had to remain liquid at extreme cold. It had to mix thoroughly with water. It had to resist separation during storage. It had to avoid corroding aluminum, magnesium, and steel components that made up the engine's internals. And, critically, it had to be available in sufficient quantities to supply an entire fighter force operating across England. Testing in Connecticut used methanol, methyl alcohol, wood alcohol, CH3OH in chemical notation. It had excellent antifreeze properties, lowering the mixture's freezing point to well below any temperature a P-47 would encounter in combat. Mixed 50-50 with water, it provided the thermal properties needed for effective charge cooling. Most importantly, extensive testing showed it didn't cause corrosion issues in the aluminum alloy cylinder heads and pistons. Ethanol also worked. Ethyl alcohol, grain alcohol, C2H5OH. The same alcohol found in alcoholic beverages, though industrial grade without the purity required for human consumption. It had similar properties to methanol, slightly less effective as an anti-freeze agent, but adequate for the operational requirements. Testing showed that either methanol or ethanol, mixed approximately 50% with water, would work reliably in the anti-detonation injection system. By July 1943, production P-47 seconds began rolling off the Republic Aviation assembly lines with the R2800-59W engine. The W designation indicated water injection capability. The system added weight. 15 gallons of water alcohol mixture weighed about 100 pounds. The tank, plumbing, regulator, and associated equipment added another 50 pounds. For a fighter that already weighed 12,000 pounds fully loaded, the penalty was acceptable given the performance gain. The 56th Fighter Group received the first water injection-equipped P-47Ds in January 1944. This was the premier Thunderbolt unit in the 8th Air Force, commanded by men like Lieutenant Colonel Hubert Zemke, who understood how to exploit the P-47's strengths. The group included pilots who would become legends: Francis Gabreski, Robert Johnson, Walker Mahurin. These men flew the Thunderbolt with an aggression that made Luftwaffe pilots reassess their assumptions about American fighters. The 56th received their new aircraft with water injection at their base at Halesworth, then Boxted, in East Anglia. The improvement seemed miraculous at first. Pilots who had flown standard P-47Ds reported that engaging water injection felt like someone had lit afterburners that wouldn't be invented for another decade. The acceleration was immediate, dramatic, sustained. In test flights, pilots found they could climb faster, accelerate more rapidly, and maintain higher speeds at altitude than any previous Thunderbolt variant. Then the engines started exploding. The first incident occurred during a training flight on February 4, 1944. A pilot from the 61st Fighter Squadron engaged water injection during a simulated combat maneuver at 25,000 feet. The R-2800 detonated violently enough that the pilot thought he'd taken cannon fire. He pulled power immediately, secured the water injection system, and returned to base with an engine that sounded like it was digesting gravel. Post-flight inspection revealed damaged pistons, scored cylinder walls, and evidence of severe pre-ignition that had cracked one cylinder head. The second incident came 2 days later. Different pilot, different aircraft, identical result. Engage water injection, immediate power increase, then catastrophic detonation. This pilot wasn't as fortunate. The detonation was severe enough that one cylinder seized entirely. The connecting rod punched through the crankcase. The pilot made it back to England on what remained of his engine, landed on foam-covered runway, and watched as ground crew counted the engine as a total loss. By February 8th, every P-47 group in England equipped with water injection was reporting problems. The 78th Fighter Group at Duxford, the 353rd at Metfield, the 355th at Steeple Morden, the 356th at Martlesham Heath. The reports followed an identical pattern. Water injection worked for a few seconds, sometimes even a minute or two. Then the engine would detonate with enough violence to damage internal components. Some pilots reported that the detonation would cease if they immediately shut off the water injection and reduced power. Others weren't so lucky and suffered engine failures that ended careers and occasionally lives. General James Doolittle, commanding the 8th Air Force, faced a crisis that threatened to cripple his fighter force. The P-47 Thunderbolt represented the majority of his single-engine fighter strength in early 1944. The P-51 Mustang, with its Packard Merlin engine and superior range, was beginning to arrive in numbers, but wouldn't fully replace the Thunderbolt for months. The P-38 Lightning, while effective at altitude, had its own mechanical issues in the cold European climate. Doolittle needed the Thunderbolt, and he needed it with every advantage available. Water injection was supposed to be that advantage. It was supposed to give American fighters the power to dominate the Luftwaffe. Instead, it was destroying engines and terrifying pilots who couldn't trust their emergency power systems when combat demanded maximum performance. The immediate response was to ground all water injection operations. Pilots could fly, but only on standard power settings. War emergency power was forbidden. The 15-gallon water alcohol tanks would remain empty until engineers determined what was failing. At Pratt and Whitney's facility in East Hartford, Connecticut, the phone call from Europe arrived like a bombshell. February 10, 1944, approximately 1000 hours Eastern Time. The 8th Air Force was experiencing catastrophic failures in the anti-detonation injection system. Multiple engines damaged. Pilots afraid to use the system. Entire fighter groups effectively stripped of their emergency power capability. The situation was critical enough that the 8th Air Force was considering grounding the entire P-47 fleet pending investigation. William Kloss, universally known as Bill, was the senior engineer responsible for R-2800 field support. His subordinates called him Bouncing Bill Kloss because of how he walked with a spring in his step, a perpetual energy that suggested he was always moving toward the next problem that needed solving. That energy was about to be tested. At 800 hours on February 11th, his telephone rang with orders that would define his career. There was a C-54 Skymaster transport aircraft fueled and waiting at Bradley Field, the military section of the Hartford-Brainard Airport. Kloss was to be aboard that aircraft within the hour. His destination was England. His mission was to determine why the anti-detonation injection system that worked perfectly in Connecticut was destroying engines in combat. He had no time to pack properly, no time to review technical documentation thoroughly, and absolutely no room for failure. If he couldn't solve this problem, the United States Army Air Forces would be fighting the air war over Germany with one hand tied behind its back. Before Kloss departed, he called Frank Walker. Walker was the engineer who had developed the initial water injection system, who had performed the calibration work that made it function reliably, who understood the system's behavior better than anyone else at Pratt and Whitney. Kloss needed information. He needed guidance. He needed Walker to tell him what could possibly be going wrong 5,000 miles from the test cells where the system had worked flawlessly. Walker asked the obvious questions. What was the failure mode? Detonation under load, Kloss replied. How severe? Engines, sometimes catastrophically. When did it occur? Immediately upon engaging water injection, or after several seconds or minutes of operation. What were the pilots reporting? The engine would surge briefly as the water injection engaged, then detonate violently enough to shake the entire airframe. Walker thought through the variables. The R-2800 engine was identical to the test engines. The carburetor modifications were production versions of the tested designs. The plumbing and fittings matched specifications. The flow rates were set correctly according to the technical orders. Everything should work. Unless. He asked Kloss one more question. What kind of alcohol were they using in the mixture? Kloss didn't know. The technical orders specified a water-alcohol mixture. 50% water, 50% alcohol. The specific type of alcohol hadn't been emphasized in the documentation because everyone at Pratt and Whitney assumed it would be either methanol or ethanol. Those were the alcohols used in testing. Those were the alcohols that worked. Walker said he would investigate. That night, while Kloss flew across the Atlantic in a C-54 that bucked through weather systems and hostile airspace, Frank Walker stayed late at the Pratt and Whitney facility. He had a theory forming in his mind, an ugly theory about what happens when well-intentioned supply officers make substitutions based on availability rather than specification. He went to the test cells. He requisitioned samples of different alcohols from the chemistry lab, methanol, ethanol, and another alcohol that he hoped desperately wasn't being used in England but feared probably was. Isopropyl alcohol, rubbing alcohol, CH3CHOHCH3, an alcohol commonly used for de-icing applications because it was cheap, readily available, and effective at preventing ice formation. Walker set up a test engine. He mixed water with methanol in the standard 50-50 ratio. He ran the engine through the power, range with water injection engaged. The R-2800 performed exactly as designed. Smooth power delivery, no detonation, cylinder head temperatures within normal limits. He repeated the test with ethanol instead of methanol. Same result. The engine ran perfectly. Then he mixed water with isopropyl alcohol, 50-50 mixture, identical to the specification. He brought the engine up to power. He engaged the water injection system. For a few seconds, the engine responded normally. Then, it began to detonate. Not severe enough to damage the test cell engine immediately, but unmistakably wrong. The characteristic sharp knocking sound that meant uncontrolled combustion. The cylinder head temperatures spiking. The manifold pressure fluctuating. Everything the pilots in England were reporting. Frank Walker had found the problem at 2300 hours on February 11, 1944, while Bill Kloss was somewhere over the Atlantic Ocean, probably trying to sleep in a C-54, transport that offered minimal comfort. Walker was staring at an engine that had just confirmed his worst suspicion. The 8th Air Force was using the wrong alcohol. Someone in the supply chain had substituted isopropyl alcohol for methanol or ethanol, probably because isopropyl was available in large quantities as de-icing fluid. The substitution seemed reasonable. Alcohol was alcohol, wasn't it? Mix it with water, inject it into the engine, prevent detonation. Except isopropyl alcohol didn't work. It couldn't work. Its chemical properties were different enough from methanol or ethanol that it actually promoted detonation under the specific conditions present in a supercharged aircraft engine operating at high altitude and high power. Walker documented his findings. He wrote up a short memorandum report, the internal Pratt and Whitney format used for communicating results to those involved on a project. The report was technical, precise, devastating. Isopropyl alcohol was unsuitable for anti-detonation injection applications. Its use resulted in severe engine detonation under load. Continued use would result in engine damage and failure. The solution was immediate cessation of isopropyl alcohol use and replacement with either methanol or ethanol, mixed 50% with water. The report reached Pratt and Whitney management at 0600 hours on February 12. By 0800, cables were being sent to every possible contact in the 8th Air Force supply chain. By 10 to 100 hours, Bill Kloss had received word through military communications that Frank Walker had identified the problem. Now Kloss just had to convince the United States Army Air Forces that the solution was as simple as changing the alcohol in the mixture. Kloss landed at an airfield in southern England on the afternoon of February 12th. He'd been travelling for nearly 30 hours, crossing an ocean, fighting weather, dealing with the peculiar discomforts of wartime military air transport. He was met at the airfield by a staff car and driven immediately to 8th Air Force headquarters. There was no time to rest. There was barely time to confirm his arrival. The briefing room was already filled with people who wanted answers. A general whose name Kloss would later struggle to remember, several colonels, multiple majors, a lieutenant who appeared to be taking notes, technical representatives from Republic Aviation, maintenance officers from the affected fighter groups. Everyone wanted to know what Bill Kloss was going to do about the engines that were destroying themselves when pilots engaged emergency power. The general opened the discussion with the directness that military officers develop when lives depend on clarity. "What the hell are you going to do about these P-47 engines?" Kloss asked his own question, the question that Frank Walker had identified as critical. "What kind of alcohol are you using in the water injection mixture?" The general stared at him. What difference does that make? In typical military fashion, the question cascaded down the chain of command. The general turned to the colonel. The colonel turned to the major. The major turned to the lieutenant. The lieutenant turned to a technical sergeant who had accompanied the maintenance officers. Each officer repeated Kloss's question. "What kind of alcohol are we using?" The tech sergeant answered without hesitation. "De-icing alcohol, sir." The general demanded clarification. "What kind of alcohol is that, Sergeant?" "Isopropyl alcohol, sir." Bill Kloss felt relief and frustration in equal measure. Relief because Frank Walker had identified the problem correctly. Frustration because the solution was so simple yet had caused so much damage. He addressed the general directly. "That's your problem, General. You're using the wrong alcohol. Isopropyl alcohol causes detonation in the anti-detonation injection system. You need to use either ethyl alcohol or methyl alcohol. Isopropyl just won't work." The room erupted in questions. "Why wasn't this in the technical orders?" "It was implied," Kloss explained, "because Pratt and Whitney used only methanol or ethanol in testing. How could the supply chain make such a mistake? Because isopropyl is commonly used for de-icing, and someone assumed all alcohols were equivalent. How long would it take to fix? As long as it takes to drain every water injection tank in England and refill them with the correct mixture." The maintenance officers were already calculating logistics. How many aircraft? Approximately 400 P-47 seconds with water injection capability spread across multiple fighter groups. How much mixture per aircraft? 15 gallons per aircraft, approximately 6,000 gallons total. Where would they source methanol or ethanol in wartime England? That was a supply question, above Kloss's responsibility, but certainly not above his concern. The general made the decision with the finality that comes from understanding that delay costs lives. Every P-47 equipped with water injection would have its tank drained immediately, no exceptions. The mixture would be replaced with a proper water-alcohol blend, using either methanol or ethanol. Supply officers would source the alcohol from whatever British stocks were available. Industrial methanol. Grain alcohol from distilleries. Whatever worked, as long as it wasn't isopropyl. The work would begin immediately and continue around the clock until every aircraft was serviced. The technical sergeant asked a question that everyone was thinking. What do we do with the isopropyl mixture we drained out? Someone suggested using it for its intended purpose. De-icing aircraft surfaces. Cleaning windscreens. Anything except injecting it into engines where it would cause detonation and destruction. Kloss remained in England for another week, visiting fighter bases, observing the changeover, answering questions from crew chiefs and maintenance personnel who wanted to understand why this had happened. He watched as 55-gallon drums of isopropyl alcohol mixture were drained from aircraft tanks and replaced with methanol water mixture sourced from British chemical suppliers. He monitored test flights as pilots cautiously engaged water injection with the correct mixture and reported smooth power delivery without detonation. By February 20th, 1944, the P-47 Thunderbolts of the 8th Air Force were flying combat missions with functional war emergency power. The advantage that American planners had designed into the fighter had finally become operational. Pilots who had feared their own emergency power systems now trusted them enough to use them in combat when German fighters pressed attacks. The impact on combat operations was immediate and measurable. P-47 pilots reported that engaging war emergency power during combat provided acceleration that German pilots hadn't anticipated. Focke-Wulf 190. As that had previously IDARS-TA, been able to make diving attacks and escape, found themselves pursued by Thunderbolts that could match their speed. Messerschmitt 109Gs that relied on superior climb performance discovered that American fighters could now climb with them when the situation demanded maximum power. The 56th Fighter Group recorded its first confirmed kill, using war emergency power, on February 22, 1944. Captain Walker Mahurin, flying his P-47D coded UNM, encountered a formation of Messerschmitt 109Gs near Oschersleben during a bomber escort mission. The German fighters had altitude advantage and initiated a diving attack on the American bomber formation. Mahurin pushed his throttle forward, engaged water injection with the newly installed methanol water mixture, and felt the R-2800 respond exactly as designed. The acceleration was immediate. Where a standard P-47 would have taken precious seconds to build speed, Mahurin's Thunderbolt surged forward with authority that closed the distance to the diving Messerschmitts faster than their pilots anticipated. The lead one, 09, pulled up sharply, trying to convert speed into altitude and escape. Mahurin followed, using the war emergency power to maintain pursuit through a vertical climb that would have been impossible on standard power settings. At 15,000 feet, with both aircraft nearly stalling, Mahurin fired a 2-second burst from his .850 caliber machine guns. The Messerschmitt shuddered, rolled inverted, and fell away trailing smoke. Post-mission debriefing included detailed questions about the water injection system. Had it functioned properly? Yes. Had there been any detonation or unusual engine behavior? None whatsoever. How long had he run war emergency power? Approximately 3 minutes total during the engagement. Cylinder head temperatures? Within normal limits throughout. Oil pressure? Steady. The system worked exactly as promised, and Mahurin's victory was credited as much to the additional power as to his piloting skill. Other pilots from the 56th reported similar experiences. Lieutenant Robert Johnson, who would finish the war with 27 confirmed victories, described engaging water injection during combat as transformative. The P-47 changed character when you hit that switch, he later explained in interviews conducted decades after the war. It went from being a heavy fighter that used its weight and dive speed to advantage to being something that could accelerate and climb with anything the Germans had. The psychological impact was significant. You flew more aggressively when you knew you had that extra power available. The 78th Fighter Group at Duxford reported similar results. The 353rd at Metfield. The 355th at Steeple Morden. Across England, at every base where P-47 seconds sat on hardstands with their newly corrected water-alcohol mixtures, pilots were discovering that their fighters had capabilities they'd only imagined during the dark days of February when the system was grounded. The combat statistics from late February through March 1944 tell the story quantitatively. P-47 groups, equipped with functioning water injection, recorded victory-to-loss ratios that exceeded groups still flying earlier variants, without the system. The 56th Fighter Group alone claimed 49 Luftwaffe fighters destroyed during the first week of Operation Argument, the sustained air campaign better known as Big Week. The group's ability to maintain high speed at altitude while escorting bombers to targets deep in Germany forced Luftwaffe fighters to engage on unfavorable terms or refuse combat entirely. March 6, 1944. The 8th Air Force launched its first major raid on Berlin. Over 600 bombers protected by 800 fighters penetrated German airspace to strike the capital of the Third Reich. The P-47 groups, now fully equipped with operational water injection systems, flew escort missions that pushed the limits of their range even with external fuel tanks. The Luftwaffe responded with massive fighter formations, desperate to prevent American bombers from striking Berlin in daylight. The air battles over central Germany that day became legendary. American fighter pilots engaged German interceptors in running fights that covered hundreds of miles. P-47 pilots reported using war emergency power extensively during combat, often running their 15-gallon water alcohol tanks nearly dry during prolonged engagements. The power advantage proved decisive in multiple encounters. German pilots who attempted diving attacks found themselves overtaken by Thunderbolts that shouldn't have been able to close the distance. Messerschmitt 109s that tried to climb away discovered that American fighters could follow them to altitude using emergency power that the German fighters couldn't match. The 8th Air Force lost 69 bombers on the March 6th raid, a painful but acceptable loss rate given the depth of penetration and intensity of opposition. More significantly, American fighter pilots claimed 82 German fighters destroyed. The P-47 groups accounted for 38 of those victories. The ratio represented a fundamental shift in the air war over Europe. German fighter forces that had inflicted unsustainable casualties on American bombers throughout 1943 were now being systematically destroyed by escort fighters, whose performance exceeded Luftwaffe planning. Assumptions. Luftwaffe intelligence officers collected pilot reports describing American fighters with unexpected performance characteristics. Thunderbolts that could accelerate more rapidly than documented specifications suggested. P-47 seconds that could sustain high speeds at altitude for longer periods than German pilots anticipated. Encounters where American fighters demonstrated climb rates. That seemed impossible given the aircraft's known weight and wing loading. The reports were initially dismissed as combat stress or pilot error. How could American fighters suddenly perform better than they had months earlier? The aircraft were the same. The engines were the same. What had changed? What had changed was invisible to Luftwaffe observers. The water-alcohol mixture flowing through the anti-detonation injection system was now methanol or ethanol instead of isopropyl. That simple correction, implemented across hundreds of aircraft during a frantic week in February, had transformed the tactical situation over Europe. The P-47 Thunderbolt had become the fighter it was designed to be, and German pilots were paying the price for that transformation. Back at Pratt and Whitney's facility in Connecticut, Frank Walker received recognition that was simultaneously gratifying and frustrating. His midnight discovery had prevented a disaster that could have crippled American air operations over Europe. Yet the recognition was internal, classified, limited to memoranda and technical reports that would remain buried in company archives for decades. There would be no public acknowledgement that one engineer's insight had saved the water injection program, no newspaper articles celebrating the problem that was solved before it became catastrophic. Just the quiet satisfaction of knowing that pilots were using a system that worked because he'd spent one night testing different alcohols until he found the one that failed. Perry Pratt, the project engineer who had overseen the water injection development, incorporated Walker's findings into updated technical orders. The new documentation was explicit rather than implicit. Water-alcohol mixture for anti-detonation injection systems shall consist of 50% water and 50% alcohol, where alcohol is defined as either methyl alcohol or ethyl alcohol. Under no circumstances shall isopropyl alcohol or any other alcohol variant be substituted. The language was bureaucratic but clear. No supply officer would make the same mistake again. The question that occupied engineers and military planners alike was why the substitution had occurred in the first place. Investigation revealed a chain of decisions, each individually reasonable but collectively disastrous. The initial technical orders specified water-alcohol mixture without defining which alcohol. Supply officers in England, faced with sourcing thousands of gallons of mixture for the new water injection system, requested alcohol suitable for antifreeze applications. British suppliers provided isopropyl alcohol, commonly used for de-icing aircraft and preventing fuel line freeze-ups. The alcohol was delivered to American air bases, mixed with water in the specified ratio, and loaded into P-47 water injection tanks. Nobody questioned whether isopropyl was appropriate because the technical orders didn't explicitly forbid it. The failure was systemic rather than individual. Engineers at Pratt and Whitney assumed that specifying water-alcohol mixture was sufficient because they only used methanol or ethanol in testing. Supply officers assumed that any alcohol with antifreeze properties would work because the technical orders didn't specify otherwise. Maintenance personnel assumed that the mixture they received from supply was correct because nobody told them different alcohols had different chemical properties. The result was hundreds of P-47 seconds equipped with a mixture that caused exactly the problem the system was designed to prevent. The incident prompted changes in how technical specifications were written and communicated. The Army Air Forces issued directives requiring explicit identification of materials and prohibiting unauthorized substitutions. Pratt and Whitney revised its technical manuals to include chemical formulas and specific gravity measurements that would allow field personnel to verify mixture, composition, Supply chains implemented quality control procedures to ensure that materials delivered matched materials specified. The bureaucracy adapted, slowly and imperfectly, to prevent the same mistake from recurring. But adaptation came too late for some pilots. Between February 4th and February 20th, when the water injection system was either grounded or using isopropyl alcohol mixture, several P-47 seconds were lost to engine failures during combat. Post-war analysis could not definitively determine which losses resulted directly from water injection problems versus normal combat attrition. The question would remain unanswered. How many pilots died because their emergency power system destroyed their engines instead of saving their lives? The number was small, certainly fewer than 10, possibly fewer than 5. But each loss was preventable. Each death resulted from a supply substitution that seemed reasonable, until Frank Walker spent a night testing alcohols in a test cell and proved otherwise. The broader impact of the water injection crisis extended beyond the immediate technical fix. The incident demonstrated that even sophisticated weapons systems could fail in unexpected ways when deployed under combat conditions. The R-2800 engine with anti-detonation injection worked perfectly in Connecticut test cells because every variable was controlled. In England, operating under wartime supply constraints with personnel who didn't fully understand the system's chemical requirements, the same technology failed catastrophically. The gap between laboratory performance and field performance became a focus of military engineering that would influence weapons development for decades. The P-47 Thunderbolt continued to serve throughout the war in Europe, eventually being supplemented and partially replaced by the P-51 Mustang in the long-range bomber escort role. But the Thunderbolt found its true calling as a fighter bomber, using its rugged construction and heavy armament to devastate German ground forces. The water injection system that had caused such crisis in February 1944 became standard equipment. Pilots used war emergency power routinely, confident that engaging the system would provide additional horsepower without destroying their engines. The 15-gallon water alcohol tank became as essential as the main fuel supply. Ground crews developed procedures for mixing and loading the methanol water or ethanol water combination with the same care they applied to armament and fuel. By June 1944, when Allied forces launched the Normandy invasion, P-47 seconds of the 9th Air Force were providing close air support to ground troops with devastating effectiveness. The fighter bombers carried bombs, rockets, and ammunition while retaining the water injection capability that allowed them to escape German anti-aircraft fire and defend themselves against Luftwaffe interceptors. The combination of heavy firepower and emergency power proved lethal. 8th Air Force statistics documented that P-47 seconds destroyed over 7,000 German aircraft during the war, with more than half those victories achieved in air-to-air combat. The remainder fell to ground attack missions that targeted airfields, rail yards, and supply columns. In both roles, water injection provided the power margin that kept pilots alive and missions successful. The post-war accounting revealed the scale of the crisis that had been averted. Between January and May 1945, P-47 Thunderbolts flew over 500,000 sorties. They dropped more than 132,000 tons of bombs. They destroyed thousands of locomotives, tens of thousands of vehicles, and inflicted casualties on German forces that measurably affected the ground war. All of this was accomplished using fighters equipped with water injection systems that had nearly been abandoned in February 1944 because someone filled the tanks with the wrong alcohol. Frank Walker remained at Pratt and Whitney throughout the war, continuing development work on the R-2800 and later engines. He rarely discussed the isopropyl alcohol incident, considering it simply part of his job to identify problems and solve them. In interviews conducted decades later, after the technical details were declassified, Walker described the night he tested different alcohols as memorable, primarily because he'd missed dinner. The dramatic implications, the crisis averted, the lives saved, these were abstractions compared to the immediate problem of understanding why an engine detonated when theory said it shouldn't. His humility was characteristic of the engineers who won the war in laboratories and test cells far from combat. They didn't fly missions over Germany. They didn't face flak or fighters. They worked irregular hours in buildings that smelled of hot metal and burned fuel, solving problems that pilots would never know existed. When their solutions worked, pilots lived, and missions succeeded. When their solutions failed, pilots died, and the engineers worked longer hours until they found what went wrong. Bill Kloss returned to Connecticut after his emergency trip to England, resuming his responsibilities for R-2800 field support. His personnel file contained a commendation for solving a critical field problem under emergency conditions, though the commendation remained classified along with the details of what had actually occurred. He continued supporting R-2800 operations throughout the war, traveling to combat theaters when problems emerged that required engineering expertise. The isopropyl alcohol crisis remained the most dramatic of these deployments, but not the only one. Engines were complex machines operating under extreme conditions. Problems emerged. Engineers solved them. The cycle continued until the war ended. The 56th Fighter Group, the first unit to receive water injection, equipped P-47 seconds, and the first to experience the detonation problems, finished the war as the only 8th Air Force fighter group still flying Thunderbolts. While other groups transitioned to P-51 Mustangs, the 56th remained loyal to the aircraft they'd learned to fly and fight. The group claimed 677.5 air victories, more than any other 8th Air Force fighter group. Their ace pilots, Francis Gabreski with 28 victories, Robert Johnson with 27, Walker Mahurin with 21, became legends. All of them credited the P-47's ruggedness and power for their survival. All of them used water injection extensively in combat, once the system was corrected. Gabreski later reflected on the water injection crisis in interviews conducted in the 1970s and 80s. He remembered the fear that accompanied engaging the system in early February, before anyone understood what was failing. He remembered the relief when Bill Kloss arrived with answers. Most vividly, he remembered the first combat mission after the system was fixed, when he engaged war emergency power, expecting detonation, and instead felt smooth, massive acceleration that let him close on a Focke-Wulf 190 before the German pilot realized pursuit was even possible. That feeling, Gabreski explained, was confidence. Knowing your aircraft would respond when you demanded maximum performance. Knowing the engineers had solved problems you didn't even understand. Knowing that American industrial and technical capability extended from factories in Connecticut to combat over Germany. The statistical legacy of the water injection system demonstrates its importance quantitatively. P-47 groups equipped with functioning water injection achieved higher victory-to-loss ratios than groups flying earlier variants. The power advantage translated into tactical flexibility. Pilots could choose to engage or disengage based on tactical situation rather than being forced into combat on terms dictated by German fighter performance. This flexibility allowed aggressive escort tactics that kept Luftwaffe fighters away from bomber formations. When German pilots did press attacks, American fighters had the power to pursue and destroy rather than merely defend. German fighter pilots interviewed after the war consistently mentioned American fighter performance as a factor in Luftwaffe decline. Heinz Baer, a Luftwaffe ace with over 200 victories, noted that P-47 seconds in late 1944 and 45 demonstrated acceleration and climb performance that seemed impossible for such a heavy fighter. Günter Rahl, another high-scoring German ace, described encounters where Thunderbolts matched the climb rate of lighter Messerschmitt 109s. Neither pilot knew about water injection specifically, but both recognized that American fighters performed beyond what German intelligence had documented. That performance gap was measured in horsepower, delivered through a correctly formulated water-alcohol mixture. The technical specifications tell the story precisely. An R-2800-59 engine without water injection produced 2,300 horsepower at military power using 130-grade fuel. The same engine with water injection produced 2,500 horsepower at war emergency power. Later versions using 150-grade fuel and improved water injection systems achieved 2,600 horsepower. The progression from 2,300 to 2,600 horsepower represented a 14% increase in power output. In tactical terms, this translated to approximately 20 miles per hour, additional speed at altitude, several hundred feet per minute, improved climb rate, and acceleration that allowed pilots to control engagement geometry. These numbers seem abstract until converted into combat scenarios. A P-47 running standard power at 25,000 feet had a maximum speed of approximately 428 miles per hour. The same aircraft running war emergency power achieved 448 miles per hour. A Messerschmitt 109G at the same altitude had a maximum speed of approximately 406 miles per hour. A Focke-Wulf 190A achieved 408 miles per hour under optimal conditions. The performance gap was narrow when P-47 seconds flew on standard power. The gap widened to decisive advantage when American pilots engaged water injection. German fighters that could barely be caught became German fighters that could barely escape. The climb rate advantage was equally significant. A standard P-47D climbed at approximately 2,800 feet per minute at low altitude. With water injection, climb rate increased to approximately 3,200 feet per minute. German fighters typically climbed faster than Thunderbolts at low altitude, using that advantage to gain position before making attacks on bomber formations. Water injection narrowed the climb advantage enough that P-47 seconds could maintain contact during the climb, preventing German fighters from establishing ideal attack positions. In air combat, the ability to match an opponent's climb rate transforms tactical options. Fights that German pilots expected to control suddenly became contests where American pilots could compete on nearly equal terms. The Pratt and Whitney R-2800 engine family produced over 125,000 units between 1940 and 1960. The engine powered not just the P-47 Thunderbolt, but also the F-4U Corsair, F-6F Hellcat, a 26 Invader, and numerous other military and civilian aircraft. The water injection technology developed through trial, error, and Frank Walker's midnight testing became standard across the entire engine line. Post-war civilian versions used for commercial aviation incorporated anti-detonation injection for takeoff power, allowing heavily loaded transport aircraft to operate from shorter runways. The technology that nearly failed in February 1944 became fundamental to aviation engineering. The broader lesson from the water injection crisis was about complexity and assumption. Engineers at Pratt and Whitney assumed that specifying water-alcohol mixture was sufficient because they understood which alcohols worked. Supply officers assumed that any alcohol would suffice because the technical orders didn't specify otherwise. Maintenance personnel assumed that materials provided met specifications because verification wasn't their responsibility. Each assumption was individually reasonable. Collectively, these assumptions created conditions where P-47 seconds flew combat missions with water injection systems that caused the exact problem they were designed to prevent. Modern engineering practice addresses these failures through redundant specification and verification. Technical orders now include chemical formulas, specific gravity measurements, and explicit prohibitions against substitution. Supply chains implement multiple verification steps to ensure materials match specifications. Quality control procedures test samples rather than assuming compliance. These practices emerged directly from incidents like the water injection crisis, where reasonable assumptions led to catastrophic results. The human element remains central to the story. Frank Walker could have conducted minimal testing, confirmed that something was wrong, and recommended further investigation. Instead, he tested multiple alcohol variants until he identified exactly which one failed and why. Bill Kloss could have requested additional time to study the problem before travelling to England. Instead, he boarded a C-54 transport within hours of receiving orders, crossing the Atlantic during wartime to solve a problem that threatened combat operations. The pilots who reported water injection failures could have simply avoided using the system rather than documenting incidents that suggested something was fundamentally wrong. Instead, they filed detailed reports that allowed engineers to recognize a pattern requiring investigation. Each of these decisions reflected a commitment to solving problems rather than avoiding them. The culture that produced these decisions was built on accountability, technical rigor, and understanding that mistakes in engineering translated directly into pilot casualties. Pratt and Whitney engineers knew that their work affected combat outcomes. Army Air Forces pilots knew that reporting problems helped engineers identify solutions. The feedback loop between combat operations and technical development operated efficiently enough that a crisis emerging in early February was identified, investigated, and solved by late February. The speed of response seems remarkable from a modern perspective, where complex technical problems often require months or years of investigation. The water injection crisis was identified, diagnosed, and corrected in less than 3 weeks. This was possible because engineers like Frank Walker had deep understanding of the systems they'd developed, because military leadership prioritized technical problems affecting combat capability, and because supply chains could be redirected rapidly when circumstances demanded. The organizational structure that enabled rapid response was itself a weapon of war, as significant as the fighters and engines it supported. The final irony is that the crisis was entirely preventable. If technical orders had explicitly specified methanol or ethanol, supply officers wouldn't have substituted isopropyl. If Pratt and Whitney engineers had anticipated that supply chains might substitute similar but incompatible materials, they could have included prohibitions in the original documentation. If anyone along the chain had questioned whether all alcohols were equivalent, testing could have identified the problem before the first P-47 flew with isopropyl mixture. Prevention required only that someone ask the right question at the right time. But prevention didn't occur, and the crisis emerged exactly as it had to. Hundreds of P-47 seconds flew with water injection systems that destroyed engines instead of providing power. Pilots lost confidence in emergency systems they needed to survive combat. The American air offensive over Europe faced a technical crisis that threatened to cripple fighter operations during a critical phase of the war. And one engineer, spending a night in a test cell, discovered that the difference between success and catastrophic failure was which bottle of alcohol you poured into the mixture. Frank Walker died in 1989, having spent his career in aviation engineering. His obituary made no mention of water injection or the crisis he'd solved in February 1944. The work remained classified long after the war ended, buried in technical reports and company archives that few people would ever read. His contribution to the war effort was known to a small group of engineers and military officers who understood what had nearly gone wrong and how close the margin had been between disaster and solution. Bill Kloss retired from Pratt and Whitney in the 1960s, his career spanning the development of reciprocating engines, turbojets, and turbofans. He occasionally told the story of his emergency trip to England, emphasizing not the drama, but the relief he'd felt when Frank Walker's diagnosis proved correct. The worst outcome for an engineer, Kloss explained in later years, was arriving at a problem without understanding its cause. Walker's testing had given him both diagnosis and solution, transforming an emergency deployment into a straightforward implementation of corrective action. The P-47 Thunderbolts that fought the air war over Europe carried no plaques commemorating the engineers who solved their problems. The water injection tanks bore no inscriptions, explaining that the methanol water mixture inside had been corrected after someone discovered that isopropyl alcohol caused detonation. The pilots who flew these aircraft knew only that engaging war emergency power provided the surge of acceleration and climb performance that kept them alive during combat. The technical crisis that had threatened to ground the fleet remained unknown to most of them, solved quietly by engineers who believed that solving problems was simply part of their job. The lesson endures beyond the specific circumstances of February 1944. Complex systems fail in unexpected ways when deployed under conditions different from their design environment. Assumptions that seem reasonable in controlled settings become dangerous in operational reality. Solutions require both technical understanding and willingness to question what everyone assumes to be true. Frank Walker's willingness to test different alcohols rather than accepting that all alcohols were equivalent saved the water injection program. His midnight work in a test cell prevented a crisis that could have affected the entire air war over Europe. The purple-dyed aviation gasoline that powered the P-51 Mustang to 490 miles per hour captures historical attention because it's dramatic, visible, transformative. The water-alcohol mixture that allowed P-47 Thunderbolts to develop war emergency power lacks that dramatic quality. It was colorless, invisible, mundane, just water and alcohol mixed in equal proportions. Yet this mundane mixture, when formulated correctly with methanol or ethanol instead of isopropyl, provided the power that allowed American fighters to dominate German interceptors during the critical months of 1944. Wars are won through accumulation of small advantages. The P-47's water injection system provided one such advantage. The speed with which engineers identified and corrected the isopropyl alcohol problem provided another. The willingness of pilots to report problems despite the grounding that resulted demonstrated a third. Each advantage was modest individually. Collectively, they determined who controlled the skies over Europe in 1944 and 1945. The R-2000, 800 engines that powered P-47 Thunderbolts through combat missions over Germany, France, and Central Europe ran on 100.30 or 150 grade aviation fuel. They breathed air compressed by turbo superchargers that maintained power at 40,000 feet. They burned fuel-air mixtures in 18 cylinders arranged in 2 radial rows, and when pilots demanded maximum power, when combat required every horsepower available, they injected a mixture of water and alcohol into the supercharger intake to prevent detonation and allow power output that would have destroyed an unmodified engine. That water-alcohol mixture had to be correct. 50% water, 50% alcohol, where alcohol meant methanol or ethanol, never isopropyl. The specifications seemed simple. The implementation required that someone spend a night testing different alcohols until identifying which one failed. That someone was Frank Walker, development test engineer, Pratt and Whitney Aircraft, East Hartford, Connecticut. His midnight discovery in February 1944 saved the water injection program, restored war emergency power to hundreds of American fighters, and prevented a technical crisis from becoming operational disaster. The P-47 Thunderbolts that flew combat missions after February 20, 1944, carried 15 gallons of correctly formulated water-alcohol mixture. Pilots engaged war emergency power, knowing the system would respond with smooth, massive acceleration instead of violent detonation. German pilots who encountered these Thunderbolts discovered that American fighters performed beyond documented specifications, climbing faster and accelerating more rapidly than intelligence estimates predicted. The performance gap was measured in horsepower, delivered through chemical engineering that worked because one engineer refused to assume that all alcohols were equivalent. Victory in war belongs to nations that can deliver technological advantage to combat forces and sustain that advantage through superior engineering, logistics, and adaptation. The water injection crisis of February 1944 demonstrated all three capabilities. American engineers developed technology that provided significant performance advantage. When that technology failed due to supply chain error, engineers diagnosed the problem rapidly. Military logistics adapted immediately, replacing thousands of gallons of incorrect mixture across hundreds of aircraft. The entire cycle from crisis to solution required less than 3 weeks, fast enough that operational impact was minimized. This was industrial warfare fought not just with soldiers and pilots, but with engineers and supply officers, test cells and technical reports, midnight discoveries and emergency deployments. The drama played out not in aerial combat, but in laboratories where one bottle of alcohol worked and another didn't. The heroes weren't necessarily the men who flew fighters over Germany, but also the men who ensured those fighters would perform as designed when combat demanded maximum capability. Frank Walker's contribution was invisible to everyone except the small group of people who understood what had nearly failed and how close the margin had been. His work saved lives he would never meet, prevented losses that would never be recorded because they didn't occur, and restored capability to a weapons system that affected the outcome of the war in Europe. The recognition he received was limited to internal memoranda and classified reports that would remain buried for decades. But recognition was never the point. The point was solving the problem. Understanding why engines detonated when theory said they shouldn't. Testing alternatives until identifying what worked and what failed. Documenting findings so that others could implement solutions. This was engineering in service of war, technical work that determined tactical outcomes, midnight testing that saved morning missions. The P-47 Thunderbolt earned its reputation through ruggedness, firepower, and the ability to absorb punishment that would destroy other fighters. Pilots loved the aircraft for bringing them home despite battle damage that should have been fatal. But the Thunderbolt's most significant advantage was power. The R-2800 engine with anti-detonation injection could produce 2,500 horsepower when pilots engaged war emergency power. That power allowed tactics German pilots couldn't counter, performance German fighters couldn't match, and aggression that American pilots couldn't have sustained without confidence that their aircraft would respond when maximum power was demanded. The find pilot, water-alcohol mixture that made this power possible had to be correct, methanol or ethanol mixed with water, never isopropyl, no matter how reasonable the substitution seemed to supply officers facing wartime logistics challenges. The lesson was simple. The consequences profound. One engineer testing different alcohols in a midnight session prevented disaster. One emergency deployment solved a crisis that threatened combat operations. One corrected specification restored capability to hundreds of fighters that would fly thousands of missions before the war ended. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.